Sample question 5.1.1 really brings in more than just the topic of Chapter 5, exo and endothermic reactions, calculating enthalpy changes, Hess's law, and bond enthalpies. It really takes us back to more of what the year would happen. We have magnesium reacting with dilute sulfuric acid, and it says that the temperature of the acid rises. And the first part that it's asking us to do is to write a balanced equation for the reaction of magnesium with sulfuric acid. Well, we know magnesium, Mg, is a metal, and like most metals on the periodic table, it's a solid at room temperature. So I can start out with that part. I know that magnesium is not a diatomic molecule. There's only 7 of those, and none of them are metals. So I know just Mg is perfect the way it is. And then that's reacting with dilute sulfuric acid. This dilute is telling me the concentration of it, and so I know it's something that is dissolved in water, so it's aqueous. And sulfuric acid is the sulfate ion, SO4 2 negative, reacting with a hydrogen ion, H+. And that's why I get H2SO4 for sulfuric acid. You may just have H2SO4 memorized, but it's always kind of handy to know where that came from. We know it's because there's an H+, a proton, like all acids have, and the sulfate ion, SO4 2 negative. Crisscross those again. And then want to make sure we write the state, AQ, for aqueous, dissolved in water. And what happens is the magnesium comes in and kicks out the hydrogen. So now I have an Mg that on the periodic table is a 2+. I know that it will lose 2 electrons to be within the same isoelectronic series as neon. And then the sulfate ion, just like before, is SO4 2 negative. Those 2's, when they crisscross, cancel out. I need overall to be a 0 charge, so I need just 1 magnesium and 1 sulfate, 2+, 2 negative, to be 0 overall. So my one product is MgSO4, and that's going to be aqueous, dissolved in water. And I could look back at my solubility charts to verify that that's true if I needed to, but I know that it is. And then the other product, anytime I have a metal reacting with an acid, so metal plus acid, I get a salt plus hydrogen gas. So that's my other product here, H2 gas. And that just comes, there were a series of acid reactions that we said, well, if it reacts with a carbonate, it gets CO2, salt, and water. If it reacts with a base, we get salt and water. This is just one of those that we memorize the standard form so that we can predict what the products are. Now let's see if it's balanced. I've got 1 magnesium on the reactant side, 1 magnesium on the product side, 2 hydrogens on the reactant side, 2 hydrogens on the product side, 1 sulfate ion on the reactant side, 1 on the product side. So this is already balanced. Saving us a little bit of time. And then the second part, part B, asks us if the reaction is endothermic or exothermic. So we look back at this part here that I kind of put in parentheses. It says the temperature of the acid rises. So as I'm putting the reaction together, it is releasing heat. When it releases heat, it is exothermic. An exothermic reaction. It would feel hot to the touch, and it's releasing energy into the surroundings. Part C says, explain what this implies in terms of the chemical potential energy contained in the reactants and the products. And all that's saying is that the reactants have a higher energy than the products. Let's write that out here. Reactants are higher in energy. So the last part says draw the energy level diagram and make sure to label the enthalpy of the reaction. So I have, this is with time, this is my energy, and I've got my reactants up here with a higher energy. React for short. Generally, and it doesn't tell us anything about it in here, but generally there is some sort of activation energy that must be overcome in order for the reaction to occur. And then down lower than the reactants are the products. So the products are more stable than the reactants are. That's why they're down lower. They're more stable than the reactants are. And then the part between the two levels is my change in enthalpy, which is a negative delta H. It's releasing energy, which is why it is negative. The second problem, 5.2.4, says approximate values for the average bond enthalpies in kilojoules per mole of three substances, hydrogen bonds, fluorine bonds, hydrogen-fluorine bonds. What is the enthalpy change for this reaction? So 2HF goes to H2 plus F2. So I look at what the different things that are being broken and formed are. I am going to take my broken bonds and subtract from that my formed bonds. Oops. So my broken bonds are from this HF here. So I have 2 moles of the HF bond. So I would have 2 times, it says here that HF has 565 kilojoules per mole of energy in it. And then that's my only bond in there, so then I subtract from that my formed bonds, and I've got multiple ones, so I'm going to put it in brackets here. I have 1 mole of the HH bond, so I have 430 kilojoules per mole. And I add to that, because I have an add there, my F2, and there's again only 1 mole of it, so I'm going to add 155 kilojoules per mole. So I could do this a couple ways. I could do the addition first and then do the subtraction. In essence, I have 1130, so 1,130 kilojoules per mole, and I am subtracting from that 430 kilojoules per mole and subtracting 155 kilojoules per mole. When I do that, when I calculate it all out, I get 545 kilojoules per